figure shows the CDF, and you have to find the expected value of x. So normally we know that the PDF, which is what we will first need in order to get the expected value. So normally the PDF is just the derivative of the CDF, but when it's a piecewise function, you have to look at what's happening at the endpoints also. So if there is a jump, which is what we have at 0, so that's the one point you have to be careful about. So in this range, when x is less than 0, the CDF is 0. So the PDF in this range would just be the derivative of 0, which is 0. Or let's first write down the equation for this graph. So it's 0 when x is less than 0. So the graph is for the CDF. And CDF is 0.5 when x is between 0 and 2. See, that's between 0 and 2, it's 0.5. And then in this range, when x is between 2 and 3, the CDF is this straight line. And we can find the equation of this line by looking that it's going through this point 2, 0.5. And this point is 3, 1. And once you do your pre-calculus, the equation for that would be 0.5x minus 0.5. And that was when x is between 2 and 3. And then when x was bigger than or equal to 3, you saw that it was a horizontal line of 1. And that was a 1 after 3. So now, when you are looking at an interval, the PDF will just be the derivative except the endpoints. So here it's an open interval, so we don't have to worry about the endpoints. So the PDF in this part when x is less than 0 will be 0. Similarly, when x is between 0 and 2, it's the derivative of 0.5, which is also 0. However, just if the PDF is, if the CDF is on a closed interval, the PDF which you get by taking the derivative is only on the corresponding open interval. This doesn't tell us what it is at 0. So to see what it is at 0, we have to see that what kind of a jump we are having. So if you look at the graph, you can look at it either from the formula or from the graph. So what we see is that suddenly at x equals 0, there is a jump of 0.5. Suddenly it jumps from 0 to 0.5. Now remember, CDF is the cumulative probability. So what this is saying is that as long as x is negative, the cumulative probability is 0. And suddenly, when x is equal to 0, the cumulative probability jumps to 0.5, which we can see from the graph also. At 0, it suddenly jumps from 0 to 0.5. So it means that the little f of 0 is actually 0.5. Because not because the CDF has jumped to 0.5, because there's a gain of 0.5. It was just before the 0, it was negative. Just before the 0, the cumulative probability was 0. But right at 0, the cumulative probability has jumped to 0.5. So it means 0 alone has contributed 0.5. So that's why when we are writing the PDF, it was 0 when x was less than 0 because there was no probability until then. But suddenly 0 alone had a probability of 0.5. But then it was again steady from 0 to 2. And so the derivative of the constant of 0.5 was 0. So no new probability is picked up between 0 and 2. Okay. So, and then between 2 and 3, the CDF was 0.5x minus 0.5. So the PDF will just be the derivative of that, which is 0.5. And once you are past 3, then it again leveled off to 1. So the derivative of that part will be 0. So that's why this part was 0.5 and then this part was 0. And again, note that this derivative taking business only tells us what's happening in the corresponding open interval. See, that's why I haven't written down what's happening at equal to 2. And we don't have to worry about that. In fact, there you could see that it's not differentiable, but the way we pick it up at the endpoints is by looking at what's going on. So the point 2 is not contributing anything because there was no jump at 2. Similarly, the point 3 doesn't contribute anything because there was no jump at 3. It was only the 0 which contributed a whole lot because there was that big jump from 0 to 0.5. So it means that 0.5 was contributed by 0. Now, observing this PDF, we see that it has only 2 non-zero paths. Here, 0.5, which is corresponding to x equals to 0, and then we have a 0.5, which is corresponding to x between 2 and 3. So most of the times we deal with a PDF which is either a discrete, completely discrete PDF or a completely continuous PDF. But once in a while, we do come across such PDFs which are mixtures of discrete and continuous. So this is a mixture of this discrete part, which at x equal to 0, the probability is 0.5. And then this part is a continuous part because this is a continuous range of x from 2 to 3. And here also it's 0.5. So whenever we have this discrete part sitting in a mixture kind of PDF, then that's referred to as a point mass. So what we say is that we have a point mass of 0.5 at x equal to 0. Now, if you think back in terms of probabilities, since this 0.5 and this 0.5 are the only 2 non-zero probabilities, what we are saying is that x will be 0 with probability 0.5, and x will be between 2 and 3 with probability 0.5. So x0 with probability 0.5, since that's a discrete situation. So there we know, remember the eventual goal is to find the expected value of x. So here, when you multiply the x value times the f of x value, so this is just 0 multiplied by 0.5. So in the expected value, this contributes as 0 times 0.5. And then this is between 2 and 3. When x is between 2 and 3 and we have a constant value, this is a uniform distribution, but this is not the full uniform distribution. It's uniform between 2 and 3 with half of the time because the probability here is 0.5. And so normally the expected value of a uniform AB distribution we know is A plus B by 2. So the expected value of this uniform distribution, which is between 2 and 3, will be 2 plus 3 by 2. But this expected value occurs half of the time because this has half the probability on it and half of the times it's 0. So 0.5 of the times it's 0, and 0.5 of the times you expect it to be 0, and 50% of the time you expect it to be 0, and 50% of the time you expect it to be 2 plus 3 by 2. Like, remember, the expected of uniform is A plus B by 2. So this all gives us 1.25, and that was choice D.